Common machine learning systems built for real-world tasks are real-time decision-making systems. They typically require millions of training steps, and once they have been trained, the model is fixed and they will not be able to adapt to novel unseen scenarios. They also do not possess the ability to adjust to human preferences. One promising direction that aims to overcome these issues is human-guided machine learning, where human feedback is integrated into the training loop. State-of-the-art approaches typically work for offline settings, where humans provide preference feedback on collected historical data. However, this cannot be used for real-time tasks. Other methods require direct expert demonstrations, which may not always be available to the general AI user. We introduce Guide, a framework for real-time human-guided RL with 3 novel designs: a dense feedback collection mechanism, a straightforward feedback grounding method that incorporates environment reward, and a model that learns the pattern of human feedback and provides simulated feedback in the absence of human trainers. It is ideal to have humans provide detailed feedback as frequently as possible. In order to collect dense, nuanced human feedback in real time, we designed a novel interface that allows collecting feedback signals that are continuous, both in time and value. The trainer hovers their mouse over a window to indicate their assessment of the agent's behavior. As opposed to prior work that only collects discrete feedback signals, our interface naturally engages humans and allows humans to express nuanced assessments, capturing a wider range of feedback. Parallel to collecting human feedback, we also need to ground it into something that AI agents can understand. Past state-of-the-art algorithms treat human feedback as the sole reinforcement signal. The policy it learns is optimized for maximal expected human feedback. However, this ignores the existing easy-to-access sparse environment reward that may still be useful for training. We propose a straightforward but effective solution. Convert the human feedback at each time step into a dense reward additional to the environment reward. This approach also enables leveraging off-the-shelf advanced RL algorithms. Human guidance can be time-consuming and cognitively demanding. In order to reduce the cognitive load of human trainers, we propose a neural network model that learns to mimic human feedback, acting as a surrogate for the human trainer. The key insight is that during human guidance, we can readily collect agent behavior data along with their assigned feedback values, which allows training a human feedback simulator. Once trained, the simulator can operate in inference mode to provide feedback in the absence of the human trainer. This model makes no assumptions about the human's specific feedback style or patterns. Instead, it learns to provide feedback consistent with the human trainer, minimizing the shift in reward distribution. We find our method to be effective on challenging tasks with complex dynamics. For example, in this 1v1 hide-and-seek game, the agent aims to learn a seeker policy that catches the hider as fast as possible. The view is partially observable and will require the agent to explore the map to find and chase down the hider. We also require the agent to directly learn from pixels, which is much more challenging given the dimensionality of visual input. To better model a general user group, we conducted the largest scaled study yet for human-guided RL. While past studies typically involve less than 10 human subjects, often including the authors themselves, we recruited 50 human participants who have no prior training on how to provide feedback. We were able to conduct these experiments within a week, enabled by our most recent human-AI teaming research platform, Crew. This is the learning progress of the state-of-the-art human-guided RL algorithm. This is Guide on the same task. This is continued training without humans using the simulated feedback model learned from humans. One might be curious if the individual differences among humans matter in guiding AI learning. To further investigate how individual differences between human trainers can affect the performance of guided AI agents, we carefully conducted a series of cognitive tests. What these tests measure includes response time, spatial reasoning, ability to predict agent behavior, etc. We found large individual differences between the human participants and discovered a strong positive correlation between the overall cognitive score and guided AI performance. In conclusion, we take a human-centric approach to studying human-guided RL, conduct research on a broader and more general group, and provide insights on when human-guided RL works best for individual humans. Our work can be extended in many exciting new directions. For example, how to fully leverage the expressiveness of human feedback, unconstrained to a single modality. How to organize an efficient team of humans and AI agents so that we can boost overall performance. There are many more questions to be answered, and we are eager to discover what is next for human-AI teaming.